Linear programming is the idea of trying to optimize some given objective function with specific given restraints. So optimize means we either want to minimize a value or maximize a value given some other constraint functions or constraint statements. What we're going to look at doing in example 4 is construct this system of linear inequalities and identify the shaded region and its corner points. And those corner points are going to play into how we actually optimize the objective function in this case. What we have is a banquet hall that offers two types of tables, 6-person rectangular tables at a cost of $22 each, and 10-person round tables at a cost of $47 each. That information right there gets us into the function that we want to optimize, which in this case is a minimization problem. So what we want to do is minimize our cost, which is going to come from the $22 per 6-person table, so we'll let that represent X, plus the $47 times each 10-person table, Y. So we want to know how many of each type of table we should rent to spend the least amount of money, given a few different constraints. So what we know is that we want to rent the hall for a wedding that needs tables for 230 people. That means our 6-person table, which can hold 6 people for every table, plus the other table which can hold 10 people per table, has to be able to seat at least 230 people. So we're going to use a greater than or equal to statement. It would be fine if we end up with more than enough seats, but if we end up with too few seats, not all of our guests can be seated. The room can have a maximum of 33 tables. That tells us that however many tables of the first type and the second type that we get, there's absolutely no way to exceed 33 tables. And the hall only has 10 rectangular tables. So our value for X, those 6-person tables, has to be less than or equal to 10. So that's the information that's explicitly stated for us in the problem. And then what we want to do is, again, minimize that cost and find what that minimum cost would be. Before we get into using Desmos to graph this system, there are two additional inequality statements that we need to add, which aren't explicitly stated but are implied. The first one would be that X has to be greater than or equal to 0, meaning we can't have a negative number of the first type of table. And similarly for that second type of table, we have to have 0 or some positive number of those. So in this case, we have 5 inequality statements that we'll graph and identify that region that we would shade, which would represent the solution to that would represent all the solutions to those systems. We'll do that by entering each inequality as an equation. And then we can pick any of those inequality statements to start off with, and then type in each of the remaining inequality statements as a restriction in a set of curly braces. So we have our system typed in. What we need to do is adjust our viewing window until we can see that picture and identify that bounded region. Our bounded region in this case has 4 corner points, 0.33, 0.23, 10.23, and 10.17. We can see each of those just by clicking on different lines until we have those points of intersection highlighted in gray. And I already have these plotted out on the graph in our notes. So each of these points of intersection represents a possible solution for minimizing our cost. What we want to do then is determine which of these pairs of values gives us the smallest possible value for this function that we're looking to minimize. So with linear programming problems, once we have this bounded region, or once we have our shaded region identified, the corner points, one of those corner points, will end up being our solution, the problem that either maximizes or minimizes our objective function. There are different ways we could go about evaluating that, but we could use Desmos to do it pretty quickly by inserting a table which will automatically populate with values for x1 and y1, and then we can click to create a third column, which would be our objective function, 22x1 plus 47y1, and we'll include those subscripts so that what we're doing is referencing the values that we plug in to columns x and y. What we want to do then is input each of our corner point values, so 0, 33, and then this table will automatically calculate the result of our function when it's evaluated at those 2 points. Oops. We'll continue to type in those remaining points so that we have our objective function evaluated for each of those xy coordinate pairs. What we're looking to do is minimize this value, so minimize our costs, which in this case happens when x equals 10, y equals 17, giving us a total cost of $1,019. So this coordinate pair and this minimized cost represents our solution to our linear programming problem. So we could say that our minimum cost of $1,019 is achieved by renting 10 of the 6-person tables and 17 of the 10-person tables. Since those were our values for x, y, and then this was our smallest possible value we could achieve for 22x plus 47y.